Hello everyone, welcome to today's video. Today we will be solving this limit. Now, this is a very hard problem. This is a fair warning at the beginning because you cannot really solve this problem just by applying a couple of formulas that you have learned. So, it is going to be a brain teaser, and we are going to apply certain approximations as we are required to apply in limits. We are going to apply some known expansions as well, which you may have studied from my calculus course, which are logarithmic expansions and sin x and e to the power x and stuff. So, first of all, notice in the sum 1 by n, and then you have this weird 1 by 2 plus 2 by 3 all the way up to n by n plus 1 thing. So first, let us denote the sum that you're given here, this 1 by 2 plus all these thing. Let us denote by Sn, okay? Sn be 1 by 2 plus 2 by 3 plus all the way up to n by n plus 1. We are doing this so that we can tackle this sum first and then go back to the original problem slowly. Now, notice Sn can be written as k equals to 1 to n in the summation k by k plus 1, correct? Then this can be written as k equals to 1 to n, and k by k plus 1 can be written as k plus 1 minus 1, right? Which is 1 minus 1 by k plus 1. Now this brings two summations, which is the first summation is k equals to 1 to n1, which is simply n, and the next summation is k equals to 1 to n 1 by k plus 1. Therefore, the first answer gives you n, and the second one is nothing but 1 by 2 all the way up to 1 by n plus 1. Now, this can be represented in terms of harmonic numbers. So, I'll define harmonic numbers in a moment, what they are and what are they called. But this sum basically becomes n plus 1 minus h n plus 1, where, so this is something new maybe for you, or you, if you already know it, that's great, that where hn is called harmonic numbers, okay? These are called harmonic numbers defined by, so you define harmonic numbers as such. So for natural numbers n, harmonic numbers would be defined like 1 by 1 plus 1 by 2 plus 1 by 3 and all the way up to 1 by n greater than equal to 1. So h0 is conventionally taken as 0. So we agree that the sum is basically n plus 1 minus hn plus 1. Why is the harmonic number important here to introduce? Because the harmonic number has asymptotic expansions. So hn plus 1 can be expanded. So as n tends to infinity, the numbers tend to be following a pattern. And in this case, the harmonic numbers can does follow a pattern. It can be expanded into as a form of an infinite series as follows, but only when n tends to infinity. That is what asymptotic expansion is all about. So hn plus 1 can be written as firstly gamma. I'll say what this is. Gamma plus ln of n plus 1, and then it goes on like 1 by 2 times n plus 1 and so on. Okay. So what is this gamma? Another new thing. So therefore, this is to be remembered. Gamma is approximately 0.577, I think, something around that. And it is called the Euler-Mascheroni constant. Okay. Very, very important constant in all of calculus. Gamma is called the Euler-Mascheroni constant, and the harmonic numbers can be represented in terms of this Euler-Mascheroni constant. So, for large n, what happens? So, for very large n, this denominator wala terms they get cancelled, right? So, therefore, you can say that hn plus 1 approximately is gamma plus ln of n plus 1, right? And this would make sense because then Sn, since n tends to infinity is already given, since n tends to infinity, our initial sum that we began with, which was Sn, right? So Sn can also be written, Sn can be simply written as, if you just put in the value, so we had n plus 1 minus hn plus 1, which is nothing but minus gamma plus ln of n plus 1. Okay. And you can simply write this as, let's say, n minus ln of n plus 1, and then you have plus 1 minus gamma. But ln of n plus 1 is also ln n because n tends to infinity. So ln of n plus of 1 minus gamma. As n tends to infinity will imply that ln of n plus 1 is approximately the same as ln of n, because n is so large, right? N tends to infinity, and is so large that it does not make a difference. Okay, so this is our sum Sn. All good. But we were actually doing this limit, which means n by Sn, and then n by Sn to the power n is to be analyzed. So now let's look at n by Sn and what this quantity could be. So obviously, if I put in the values, I see that n by Sn is nothing but n minus ln of n by n plus 1 minus gamma by n. Okay. And this would mean then I can write it as 1 divided by 1 minus, okay, I already divided, right? Okay, sorry. So just skip this step, and now I'm dividing, obviously. So ln of n by n plus 1 minus gamma by n. Yeah, so this is what we should have after dividing. Okay. Again, since you understand ki this is the n is very large, right? Since n is very large, we can understand this ln by n and 1 minus gamma by n, that is going to be small. Okay. Because n tends to infinity. So this limits individually go to 0. Ln by n goes to 0, and 1 by gamma minus n individually go to 0. And we know that for x tends to 0, 1 by 1 plus x is approximated as 1 minus x. So this is just first two terms of the expansion of 1 by 1 plus x, right? So we can also approximate this thing as 1 plus ln of n minus of 1 minus gamma by n. Because the plus turns to minus, and the minus turns to plus. Okay. So yeah, then we can finally say, therefore, n by Sn can be written, all of this in limit n tends to infinity, obviously, 1 plus ln of n minus of 1 minus gamma, then divided by n. Now comes the part where we want to find out n by Sn whole to the power, right? Now that is going to be a challenge, because usually what happens is this. So this resembles what form? This resembles the form when n tends to infinity, we usually have 1 plus. So if you have some xn by n whole to the power n. So this is something that can be resembled like it. Okay, by the way, we have this and not the whole thing. So 1 outside plus this. So this was this, obviously. It's just a mistake of writing. Okay, so when n tends to infinity, we essentially have something of this form where 1 plus xn, where xn is a sequence of natural numbers, sequence basically defined by natural numbers divided by n whole to the power n. Okay, but the thing is, even though when we have this, we cannot use the limit approximation, since we know that 1 plus x by n whole to the power n as limit n tends to infinity, limit n tends to infinity is equals to e to the power x when x is a constant, right? When x is a constant. This is what we know. But here ln of n minus, so here what happens here, xn is nothing but ln n minus 1 minus gamma, which is not a constant. So what we can do is this. So we want to find out n by Sn whole to the power n, right? We want to find out n by Sn whole to the power n, which is 1 plus ln of n minus 1 minus gamma by n whole to the power n. So we can take logarithms on both sides now, because as we understood that we cannot apply this formula directly. So what happens if we take logarithms? So ln of, so basically we want to now find ln of n by Sn whole to the power n, which should be n into log of 1 plus ln of n minus of 1 minus gamma by n. And you understand that this can again be broken into the series of log of 1 plus x, since this ln by n and 1 minus gamma by n go to 0. So you can write this as n whole into ln of n minus 1 minus gamma by n. This is x. And then you have minus x square by 2, which is ln of n minus 1 minus gamma whole square, whole square by 2n square, and so on. So we are using the expansion of ln of 1 plus x, which is x minus x square by 2 plus x cube by 3, and so on. Okay. Now, multiplying by n out, you simply get ln of n minus of 1 minus gamma minus ln of n minus 1 minus gamma and then whole square, not there, by 2n, and so on. Correct. Now, all of these limits go to 0 as n tends to infinity. We are pretty much clear about that, right? Because all of these logarithm terms are dominated by the polynomial terms n. Therefore, we can say ln of what we started with here, n by Sn whole to the power n by Sn whole to the power n is approximately ln of n minus 1 minus gamma. That much is clear now. And this would mean that we can now exponentiate both sides, and we can find out, therefore, n by Sn whole to the power n is approximately e to the power ln of n minus of 1 minus gamma, which is nothing but n divided by e to the power 1 minus gamma, or in other words, n into e to the power gamma minus 1. And the limit we wanted to find was this. Therefore, limit n tends to infinity 1 by n by Sn whole to the power n, where Sn is defined as I have defined before, is nothing but limit n tends to infinity n by n e to the power gamma minus 1, which is nothing but e to the power gamma minus 1, which is our final answer. So yeah, a very good limit with applying, and the problem is obviously not from high school, and this kind of problems are something that you might find at the end of a very hard real analysis course or something, in undergraduate or postgraduate level, and also in research papers. So yeah, it was something I wanted to show. So I hope you learned a lot of things from this video. So if you're new to the channel, do subscribe. And if you want to enroll to the calculus course, you can check out the description for the website link and for the app link. And if you have any comments and queries, let me know. Thank you.